Last video was pretty boring reversing, and I also told you that I gave up and looked at the write-up, which told us that the main component in the key verification check is RSA encryption or decryption. I was really surprised because I was not able to find out that it's RSA, but now that I know it's RSA, I don't just want to write the Keygen, I want to understand how RSA is implemented in assembler here, so that I learn, and in the future I will then be able to recognize RSA again. So let's head right in. We have encountered RSA on this channel before, and I recommend to watch that one as well to learn a bit more about it. But let's have a quick look on the Wikipedia page again. RSA has a public and private key, and at the heart of the RSA encryption or decryption is a modular exponentiation. To encrypt, you take the message, which you convert to a number, and raise it to the power of the public key modulo the public exponent n. And to decrypt, you raise the encrypted message to the power of the private key d modulo n. So what we basically are looking for in assembly is simply an algorithm that implements exponentiation with modulo. Modular exponentiation is a type of exponentiation performed over a modulus. The problem with this simple math is that our CPU only has 64-bit registers and not really instructions for exponentiation or modulo. So these have to be implemented by an algorithm. Not only exponentiation has to be implemented by an algorithm, but we are dealing with large numbers that don't fit into 64-bit, so you can't simply add two numbers that are much larger with simple instructions. And apparently all of this is what is implemented here. So the approach that I took to understand the assembler code was to meet in the middle. This image shows a function call tree from here. Here's our function we enter, and these leaves were the super simple functions without any outgoing ones. So they can be understood in isolation. During my own failed analysis, I actually reversed these very simple functions, but I couldn't see the wider context of it, what they are used for. So I will show you what the simple components do, and then we research basic modular exponentiation algorithms and see if we somehow get the wider picture. So here's the function that is supposedly implementing RSA. Let's follow the references of unknown functions until we reach one of the simple ones. Okay, this is a simple loop and has no other outgoing functions. So here we have a clear for loop again. Initialize I with 0, increment down here, and the condition is comparing I to the value coming from a parameter. So that parameter is clearly a length. And inside the loop we see that I is used as an offset into some buffer. In fact, it's used to load a byte from two different buffers, so we can take that as buffer 1 and buffer 2. And these were also our parameters. So we take that byte and then we add it together. Then we load some other byte, which is initially set to 0, but down here we can also see it is set again. So let's call it temporary value for now. This value is moved around a bit, but then in the end added onto the previous add result. Then we find another temporary value. It's always written here and used here, so we write that add result of those bytes and that one temporary value into it, but load it again, shift it by right by 8, and move that result into the first temp value. So if our add result was larger than 1 byte, so if there's something left after the shift right, that is what is stored in the first temp value. Then we load the add result again, only take 1 byte from it, so these are the lower 8 bits, then, and move that into the offset of the first buffer. That is a very clear add implementation for large integers. Integers that span as many bytes as you want. Was this too fast? Do you not understand how this is implementing an addition over large integers? Let's do it again while at the same time we do some elementary school math. Let's say you want to calculate 151 plus 272. How do you do that in elementary school? You write it like this, and then you go digit by digit. So 2 plus 1 is 3. Boom. 7 plus 5 is 12. So that is more than a digit. So you know what you have to do? You have to cut it off here. Take the 1 as a carry, remember it for the next round, and just keep the 2. Then comes the last digit. 1 plus 2 is 3, but we also have a carry of 1, so we add 1 and the result is 4. 423. Now quick recap of the assembler code. We load 1 byte from each number it's like a digit, we add it together, we check if we have a carry that we have to add as well, right? So that's the carry. Then we do the shift right of 8 bits, which would now get anything that doesn't fit into the byte into the digit. We cut off this byte and remember this cut off part in the carry for next round. And we only write down the byte that we just cut off in the first buffer as a result. Makes sense, right? Super simple. So we can change the type and name of this function. The first two parameters are the two numbers a and b, and the last parameter is the length of the buffers that hold a and b, and the function is simply called add. Now when we back out, we find another unknown function, but that one does a bit more, though it also has a reference to another simple function. This one looks super similar, and we can very quickly assign the same variable names as before. This is I, the length, the carry, and so forth. Instead of a simple add, we see an add and a subtract here. Could this be simply a subtract function? But why then an add? So let's see, the subtract is done R10 minus EDI, and R10 is loaded from RCX plus an offset. The offset is I and RCX is the first buffer. Okay, so a byte from the first buffer is taken and subtracted by EDI. EDI is coming from this add. EDI here is the byte from the second buffer, and R11 is from R8, and R8 is from DI, and DI is from SEL, and SEL is the carry. So we do byte 1 minus byte 2 plus the carry. That's exactly like elementary school math again. If we have a carry, we add the carry basically to the second value we subtract and subtract it from the first. So yeah, this is simply sub. We can also change the type here, a minus b, and the length of the buffers. Cool. So we understood these functions. Like I mentioned at the beginning, I figured that out on my own before I knew it was RSA. And so now you are on the same level. Next, I want to research how RSA, or better to say modular exponentiation, could be implemented. Actually, from a hardware security lecture at university, which I also mentioned in a video where I introduced hardware side-channel attacks, I already introduced such an algorithm, exponentiation by squaring. Let's check out Wikipedia. Exponentiating by squaring is a general method for fast computation of large positive integer powers of a number. And here it shows how it's done. If you have x to the power of n, you perform this recursive algorithm here. If the exponent n is even, you just square your base x, and if your exponent n is odd, you also square the base, but also multiply the base to it as well. And then the result is the new base, the new x, and you update the power. This is defining a recursive algorithm, but it can also be written as an easier iterative loop, especially when you work with bits, because in binary the number is even when it ends with a 0 and odd when it ends with a 1. And division by 2 in binary is basically just removing the last digit, right? So in binary you just go through each bit, and on a 0 you simply square, and on a 1 you perform a square and multiply. This means the pseudocode of it looks like this. For each bit of the exponent, we perform the squaring, but if the bit was 1, we do an additional multiply. So if we look again at our function, we should maybe find that. Let's first define the parameters of this function. If we assume this is RSA, then the first parameter here, which we call randomBuff at first, is in fact the RSA modulus n. And this is the public exponent e. So we can also name the parameters of this function now. Modulo n, the length of n, e, the length of e, the empty buffer, which will probably be our result, and the user input data, that is our cipher message we will decrypt. Let's go into the function and also name the local variable based on the parameter names. XOR ESI will zero out ESI, so this memset will zero out the result buffer. Then we have a memcopy, and it copies the data, our user input, into a new buffer that was allocated on the stack here. You see how it subtracts from the current RSP value, so it makes space on the stack. Then we have a for loop, init I equal to 0, and the loop condition depends on the length of the exponent buffer. So the length is loaded, shifted left by 3, that is equivalent to a times 8, and then we compare it to I. Because e is 101, that's the e length 3, this loop goes from 0 to 3 times 8, so 24. Then inside the loop, we have seen this kind of pattern before in the base 32 encode algorithm. Here we load I and divide it by 8, so that will be 0, 1, and 2, which will be used to load a byte from the E buffer. So for example, this will be 0 for the first 8 iterations of the loop. And then here I is masked with hex 7, so that is a modulo 8. And then a bit is shifted by this value. So this produces the same pattern like in that other video. So here we go over each bit of the public exponent. And if the bit is set, we execute this part. If it's not set, we skip it. Does this remind you of something? Look at the pseudocode again. Here it says we go over each bit of the exponent and then we execute the multiply if the bit is set and square every time. That is the same loop pattern here, or is it? It's the same function, it's not different. Like one is square and one multiply. And don't call me stupid now. It took me a bit to remember, but eventually figured it out. When you square x, you can also write x times x. So there you have a multiplication. So this function should be multiplication including modulus. It does take the modulo n as a parameter, and the outer function here doesn't appear to do the modulo. Let's look into that function and start again by naming the local variables based on the parameters we pass to it. We know that these two buffers hold the data that is being multiplied, so that's a and b, and this unknown buffer will probably hold the result. Then we have another for loop, and the same pattern of multiplying the condition length by 8, and here divide by 8 and shift up to 8. So this is again checking single bits, and the buffer it is checking is b, so this loops over the bits of b. If the bit is set, it will call this add, and otherwise always add here. That is kind of similar to the modular exponentiation. There we looped over bits and multiplied to achieve the exponentiation. And here we loop over bits and add numbers to achieve, hopefully, multiplication. So how can you multiply by adding? Well, let's see what is being added. Okay, we know the result, but what is var 38? It was used up here in the memcopy, so it holds a copy of the number a. So in every loop, we do a plus a, so we double it, and if a bit in b is set, we add this a to the result. If you don't see how this also implements multiplication, we have to go back to elementary math. Let's multiply two numbers, 123 times 102. So first we have to do 1 times 3, 2, 1, then 0, then 2 times 3 is 6, 4 and 2. Then we have to add these up. 12,546. Okay, so here is an adding step involved. And that is actually the same that is happening here. Let's do an example with binary numbers, then it becomes clear. Let me also kind of do it in reverse order, so we start with the first bit, not the front. We find the first bit, which is set, so we note down 0101, and then we have a 0 we note down, and then another 0101. Now if we compare this to our loop, we could have this first step added the current a to the result, so that's this line. Then we could double it, and in binary doubling the number is just shifting it by 1 to the left, so we add a 0 at the end. So see where this is going? Then in the next loop we look at the third bit, where we now add the doubled value, and the doubled a value in this case is now 10100. I hope I made it clear. So this clearly implements multiplication. However, what is the other function? It takes the intermediate result and the modulus. So I guess that one implements the modulus. Let's name again the local variables and have a look at the obvious for loop. Though this time the for loop initializes with the length and counting down to 0. And in the loop we see that a byte from a and the modulus is loaded and compared. Quick reminder. The modulus was the buffer with the random looking data, so it goes over each byte from the front comparing the current value to the modulo. If the value byte is smaller than the modulo byte, then that means the whole number is smaller and we just leave the function. If the byte was larger, then our value is larger, which means the modulo has to be applied, and it does that here with a subtraction. It's subtracting the modulus from the current value. But if the bytes were the same, we keep looping until we find a larger or smaller byte. So essentially, this is just a check if the value is larger or equal than the modulus, and if that is the case, we subtract it. That means if our value was more than twice the modulus, then this wouldn't quite work, but that will never be the case, because this is done in a loop constantly with only additions before, so immediately when the add makes the value larger, it will cut it back down. Amazing how we covered all functions and we finally were able to see that, yeah, this implements RSA. I have never looked so closely at algorithms that implement exponentiation, modular, or multiplication with large integers in assembler, so maybe I would have solved it if I had known that before. But as you know, it's all about learning and studying new things, and so even the fact that I surrendered and looked up the write-up doesn't matter. I'm super happy that I was able to fully understand it now, and I'm sure I will recognize RSA and assembler next time. This is what CTFs are for. So indeed, we have RSA decryption here. Our DLC unlock code, at least the first 12 bytes, is encrypted text, and then we compare the encrypted data to the buffer that was created before. The buffer was combined with the XORed last bytes of the unlock code with the PwnAdventure 3 string. Now all that is missing is to use everything we learned about the key verification and create a Keygen. But this video is getting pretty long, so I will create a short additional video just implementing the Keygen, and I will release that in a few days, so you have the chance to implement your own Keygen now.